Hello everyone, thank you for joining today's webinar. I am Sumit Singh, an electric motor expert at EMWorks. Today's webinar topic is virtual prototyping of 50 kilowatt high torque wind turbine generator. Here is today's agenda. First, we will go through the overview of a wind turbine generator and then look at its advantages and design challenges to design a wind turbine generator. Then we will look into its design specification that we're gonna use today for the design analysis, and then we will go through its no-load, on-load simulation analysis done using the EMWorks Motor Solutions software. And later we will demonstrate you the wind turbine electric generator using our software EMWorks 2D. Wind energy is one of the best technologies available today to provide a sustainable supply to world development. In terms of the generator for wind turbine application, there are different types of wind turbines such as fixed speed wind turbine and variable speed wind turbines. In fixed speed wind turbines, induction generators are used but it has the limitation of low efficiency and poor power quality. In variable speed wind turbines, permanent magnet synchronous generators are used, and these machines are energy efficient, high power density, and robust rotor structure. A permanent magnet synchronous generator is a generator where the excitation field is provided by a permanent magnet instead of a coil. The term synchronous refers to the fact that the rotor and magnetic field rotate with the same speed because the magnetic field is generated through a shaft mounted permanent magnet mechanism and current is induced into the stationary armature windings. Synchronous generators are the majority source of commercial electrical energy. They are commonly used to convert the mechanical power output into the electrical power for the grid supply. As we can see on the picture right hand side of the slide, there is an inflow of wind and which makes the shaft or the rotor of the wind turbines to rotate, and then the rotor and blades spin the main shaft as shown in the figure, which is termed as C, and the gearbox D helps to step up or step down the speed of the generator, and then the generator results into an electrical output. Also, we can see the actual permanent magnet wind turbine generator used by the industries. For our today's presentation, we are using a direct drive wind turbine generators. Direct drive refers to a type of wind turbine design that eliminates the gear in a conventional wind turbine. There are various advantages to use this direct drive design. One is that it increases efficiency. Some of the kinetic energy from the wind is lost in the gearbox, as is always true when steps are added to energy transmission, the efficiency gets reduced. Another disadvantage is that by using permanent magnets in the generator rather than electromagnets, it is possible to make the generator lightweight for its size, and this plus elimination of the gearbox reduce the weight of the apparatus. Therefore, the overall design becomes simpler. This is important for offshore wind power design, where the weight must be supported on a floating surface. The third advantage is that with fewer moving parts, direct drive design is less complicated to maintain and its maintenance costs are reduced over the long term. Again, this is especially important in offshore wind farming because of the difficulty in maintaining generator at sea. However, there are disadvantages of using direct drive design, as it currently exists lies in the permanent magnets used to generate the power. Permanent magnets depend on the rare earth material for their manufacturing, and these rare earth materials are available primarily from China, which is the producer of 95% of the Earth's supply. This leaves the international community dependent on China for its continued production of wind power, with possible consequences. Well, several challenges arises while designing a direct drive wind turbine generators. First, due to its high torque requirement, the overall weight and the size of the generator grows rapidly and it becomes heavier. Therefore, a design needs to be smaller in size with higher torque density with reduced weight. Second challenge is to design the air gap to handle its flux density requirement and also to eliminate the possibilities of the rotor and the stator cores getting rubbed between each other under any kind of operating conditions. Third is the dynamic short circuit forces, which need to be accommodated within the limits of the minimum air gap. EMWorks Motor Solution provides user to design a generator with analyzing its electromagnetic performance, thermal performance and structural performance. First, we have MotorWizard tool. It is a template-based motor design software that allows user to accurately solve both electric and magnetic problems. Second, we have EMWorks 2D tool. It is a 2D electromagnetic simulation software that uses the finite element to solve magnetic, electric and transient problems. It allows users to study the effect of geometry or simulation parameters changes on the design. It also allows to couple a transient magnetic study to mechanical motion and thermal. Third, we have EMS tool. It enables user to do both electrical and magnetic simulations using the complete 3D geometry. EMS is a true multi-physics software that enables user to couple the magnetic and electric design to circuit, motion, thermal and structural analysis on the same model in a hassle-free integrated environment. So today we will be using these tools to design the electric generator for our wind turbine application. So moving on to the design specification, we are going to design a 50 kilowatt high torque low speed permanent magnet generator whose outer diameter is 1800 mm with the stack length of 165 mm as we can see in the 3D diagram. The number of slots is chosen to be 120, whereas the number of poles is 116. The coil turns were kept as 19 number of turns with the air gap of 5 mm. The mechanical speed at the base is set as 51 rpm with frequency of 50 Hz. So moving on to the simulation and results. First, we have no-load analysis. We can see the magnetic flux density plot at the base speed of the generator using the software EMWorks 2D. And through this plot, we can understand the point of saturation in the generator. On the right hand side, we have shown the cogging torque plot versus time at the base speed of the generator. As it's a high torque machine, the cogging torque for this type of design usually will be higher, and as we can see it's close to 25 Newton meter, which is close to 0.25% of the rated torque. Next, we have the back EMF of the generator. As the generator was rotated with its base speed of 51 rpm, the induced voltage is generated across the stator terminal of the generator. For our design, the peak phase induced voltage is close to 210 volts. On the right hand side, we have a flux linkage waveform for our generator. The peak phase flux linkage is close to 0.7 Weber. Here we also analyzed our generator's performance with a resistive load connection. For its performance analysis, all the three phases of the generator were connected to a 1.2 ohm load, resistive load in star connection fashion. And we can also obtain the magnetic flux and current density plots using the software as shown here. The maximum flux density in our generator design is close to 1.5 to 1.6 Tesla, and the current density is close to 1.3 ampere per meter square. Next, we have the plot for the speed versus time. Therefore, we have simulated our design for a constant speed of 51 rpm and try to obtain its torque versus time plot. Here we can see, as we are simulating generator model, the torque generated is represented in negative form and it's close to 4700 Newton meter. For our design, the rated torque is close to 9200 Newton meter. As the partial load is connected at the stator terminal of the generator, we have a torque around 4700 Newton meter. Next, we have current variation versus time and the terminal voltage versus time. So, based on the load connected at the stator terminal of the generator, the current has been induced in the stator winding, and we can see its peak magnitude for each phase is around 120 amperes. The current generated by this generator is purely sinusoidal in nature because of its high slot and pole number design. On the right hand side, we have a terminal voltage of the generator, which is obviously lesser than the back EMF generated, as we have a drop across the stator winding. Next, we have obtained the losses in the winding of the stator. Its magnitude is close to 1400 watts, and we can also obtain the winding losses density for each slots of the stator. Then we have also obtained the losses occurred inside the rotor core and as well as the stator core. As we can see on the left hand side, the stator core losses is around 550 watts, whereas the rotor core losses is very less and close to 25 watts. We can also split the core loss components into its eddy current losses and hysteresis losses as well as excess losses. So the total loss which we obtained for the stator core as shown in the left hand side, which is close to 550 watts, are splitted, and we can see its eddy current is close to 225 watts, and then we have the hysteresis loss which is close to 200 watts, and then the remaining excess loss is 125 watts, and therefore sum of all these core loss components leads to the total core loss of the machine. Next, we have also performed its 2D thermal analysis, which is also one of the key factor to analyze apart from the electromagnetic simulation analysis. Therefore, the EMWorks Motor Solutions software helps the user to obtain the thermal performance of the machines. Therefore, we can observe its instantaneous temperature distribution in the winding is as shown in the left hand side of the figure, and the temperature is close to 120 degrees Celsius, which is well within the limit of the insulation grade, and also we can obtain its temperature distribution for rotor. Next, we have performed the thermal and structure analysis but for the 3D geometry. Therefore, the 2D geometry was extruded to its stack length of 165 mm, and then its 3D temperature distribution losses generated due to stator winding is obtained, which is close to 128 degrees Celsius, and also the thermal stress distribution was obtained, which as can be seen on the right hand side of the figure. It is also very important to analyze the stator deformation under the thermal stress effect. Therefore, for the overall stator, the displacement was around 0.2 mm, but just looking at the stator deformation for a particular stator core, the total displacement was around 200 micrometer. So far, we have obtained the performance analysis of a high torque low speed permanent magnet generator using the EMS 2D software, where we observe its back EMF, cogging torque, electromagnetic torque and the losses, and also we have used an EMS software to get its thermal and structural analysis. Now, once we know the D-axis and Q-axis inductance, which can be obtained either of the software, we can use these magnitudes to further analyze and get the performance of the motor without the need of the geometry. Here we have obtained the D-axis and Q-axis inductance as for the machine as in the motoring mode, and we can see how the inductance value decreases as we increase the current. Therefore, using the MotorWizard tool, a user can feed the parameters such as flux linkage, D and Q axis inductance, the rated current and the speed of the machine, and can quickly get the efficiency map of the machine within a seconds. And next we have the motor versus torque speed as shown in the figure. So here's a quick demonstration which shows how a MotorWizard tools can be used to quickly generate the performance curves. So once we are into the MotorWizard tool, select performance calculator, where we have selected the brushless permanent magnet motor, and we need to enter this equivalent circuit parameters as shown in the previous slide, the core loss parameter and the operating parameters. Then we go to calculator section and select the performance and click on the calculate to obtain the performance results. So let us look at the voltage versus speed curves. So we have a D and Q axis voltages. Then we can also obtain the D and Q axis current, the torque versus speed of the machine, also the power versus speed, and finally we can obtain its efficiency map as shown here. And user can also obtain the magnitude of efficiency at different points by just clicking or using its cursor on the map. So in today's webinar, a scaled down model of a 50 kilowatt high torque wind turbine generator was designed, and we have used EMWorks tools which provide a complete and full solution for electric machines, including electromagnetic, motion, structural and efficiency analysis to validate its performance. The model studied in today's webinar helps the user to understand the working principle of a wind turbine generator and also to understand the generation of torque for different types of load, and also to understand the losses generated in the stator and the rotor cores as well as the structural deformation. And now all the participants can use the chat box option to ask the questions. Thank you so much.